Hey, welcome back. So, I guess it's almost the time that we wish a safe flight to Parvati that is going to board our plane soon. And it's also the time that we will start our last 40 minutes of today. So, let me keep an eye on the chat in case you found some questions. I see no questions, so I will just go on, and maybe there is some time for questions at the end. We will see. So what have we done? We have looked into three forms of prediction. That was regression, classification, and clustering. The regression, we looked only actually on the linear regression, but I mentioned that it can be for more complex shapes, more complex curves than a straight line. We looked into classification using decision trees or classification trees, and we looked into clustering using the k-means algorithm. And then I said that after the break, we would look into how do we measure the accuracy of these instruments, and what are the criteria that we should obey in order to decide whether a predictor is good or not. And that going blindly for the highest accuracy could be a fallacy. That's what we just said. So that was before the break. So I said already that indeed, when you have like a data set and you are doing regression, you can do a linear regression, or you can use more complex shapes. And these complex shapes are typically like polynomials. And as you know, a polynomial of degree 3 may have like two of these inflections, and a polynomial of degree 20 may have like many of those. So it can be very complex curves. And as you are seeing, the higher the degree of your polynomial, the better it is able to actually follow your data set with many convolutions. I mean, the way of learning will lead to being able to describe the data set very well, but you want to use such an instrument, in fact, to predict values outside the data set. And if those values actually happen to be outside like this interval where you have observed the previous one, so you find the value which is higher than the previous ones or lower than the previous ones, then you probably or start already suspecting that having such a very wavy curve will lead to unpredictable behavior when you are predicting outside the support of your data set. So there is this risk of overfitting because the more your predictor can describe the training set, the bigger the risk that it will actually overfit, and hence the name, to that set of data and become blind to new sets of data. So it's a kind of a trade-off. And the trade-off is hard to make in general, but requires some experience. But it relates to notions that I will explain a little bit later, the notion of bias and the notion of variance. In fact, overfitting in regression and in general is typically alleviated with more data. So if you have a small data set, the risk of overfitting, if you increase the degree of this curve, is higher for a smaller data set, because you see that the curve is going to follow almost all the individual points, than it is for a bigger data set. Because even if you allow your curve to have a higher degree, it will behave like a curve of a smaller degree in a data set with many more points, because you have many points pushing the curve back and forth, and that it will follow more or less indeed a kind of a pattern in the middle, as you would like it to do. In classification, you can get very complex trees that, of course, that what I'm drawing here is not exactly what a tree does with only horizontal and vertical splits, but you get the picture that if you are able to have very deep trees, and in order to see that in action, you just go to your notebook, and you ask your tree to be very big, like depth 12, then the tree itself becomes very complex. It is able to describe the training set without any mistake at all. I mean, does not make any misclassification. And if you look at the data set, you already imagine that it's going to be very convoluted because it's going to completely separate the greens for the oranges and the greens from the reds. It's going to be very convoluted. And you see it's a very complicated tree, but it's a perfect description of the training set. Whether it is a good instrument to predict new fruits, it's open for debate. And typically what you see is that you can do indeed underfitting. This is too simple. There is too much variance on the outcome. This is probably, I mean, this is just very rough drawings. This is probably like a good fit, and this will be like overfitting. And yeah, it boils down to very wise principles, like Einstein also said that everything should be made as simple as possible, but not simpler. In fact, Einstein was not the first to say some things like that, because William of Ockham many years ago already said more or less the same. But okay, so there is also a problem if you oversimplify. One of the simplifications we do in data science is called dimension reduction. So basically what we do is that we may end up losing some parts of the data for the sake of being able to do more with the data that we decide to process. And it may be risky. And suppose that the image that you are given to watch is this one. It's clearly a shadow of two people. You may lead to take the wrong conclusion, but if you see the whole picture, then you see that they are actually passing by each other, and the shadow just led to that specific interpretation over there. So this is a very visual way to tell you that you should not simplify as well. But when it comes to these instruments like regression, classification, and clustering, for instance, one example of simplifying too much is to treat data that actually comes from two different categories as if it was one single category. So doing this will give a very reasonable fit, but if you would have done regression on the categories individually, it will be much more correct, like this blue line and this red line in opposite to the single black line. If you go to the notebook that you have been given, you have, like in the linear regression case, you can either oops, I should run it, of course, in order, and I have many things that I haven't run yet. You can either do the regression based on the whole set, and then you get like this, or suppose that you regress only on one of the clusters, then it's clearly a better fit of your regressor with your data. So one example of oversimplification is to ignore that the data is clustered. And these errors you may make manifest in two ways. There is what we call bias, and bias is when there is a kind of a tendency of deviating from the true values. So we have here that the predictions, those blue dots are the predictions, the red dot is the true value that you want to predict. And of course that when you are bullseye, you are doing the right thing, and that's what you want. You want to have low bias, low variance. Here you have low bias, high variance, meaning that you are getting around the right value you want to predict. Here you have low variance, like you have all these predictions very concentrated around each other, but they are far from the true value because you have high bias, and here you have both high bias and high variance. So when you observe bias and variance, they are kind of measures of deviation, and you would like to have ideally the lowest bias and the lowest variance, but this is very hard to get, if not impossible, in true data science. So bias and variance relate to underfitting and overfitting. So if you have like an ideal fit in opposition with an underfit of an overfit, The bias is higher when you have underfit because you have like maybe some tendentiously values that are estimated by a smaller estimate than they really are, or by a higher estimate than they really are. Why here you have a very low bias, and here you have both low bias and low variance. But low variance is typically a very clear indication of possible overfitting. Okay. All this can be actually alleviated with a very simple strategy. And the simple strategy is to train your instrument not on one single set of data. So if you have a very big collection of historical data, you will split it into two sets typically, one that you use to train, another one that you use to test. And if you are doing supervised learning, the test set will allow you to see whether the predicting ability of this instrument is able to indeed predict correctly for values that he has not seen. So this we did on the notebook. On the training set, we are also measuring the accuracy of our classifier inside the set, and we were misclassifying a few oranges. This we haven't done yet. That's what we are going to do when you divide your historical data in two sets, one for training your instrument or learning from it, another one to test it. And this is just to validate whether your instrument has the ability to predict values that he hasn't seen before. And if you do this with different training sets from the same historical data, and you observe different predictors, and you take that one that behaves the best, you are actually lowering both the variance and the bias. But it requires that you have enough historical data. And you should actually allow these training sets to be sampled from the historical data in some kind of random way. If the historical data reflects chronological data over time, it will be an obvious mistake if you'd say, okay, I'm going to train on the oldest data and test on the newest, because you never know whether the phenomenon at hand changed over time. So the most, let's say, the most harmless way of dividing your historical data into two sets is actually taking random sampling. And we come back to statistics when we talked about samples and the importance of getting the right sample in order to do inference for your data. So your training set leads to a model, your test set is fed to the same model, and then you measure the quality of the predictions by comparing the predicted values with the true values. So there are two error measurements that you can make. The training errors, you can actually bring them to zero because you can do overfitting. This is the result of overfitting, bringing the training errors to zero. Think about clustering. When you cluster complete data into individual clusters, and the errors made are zero. When you do overfitting in terms of the complexity of a tree, you can also describe the training set completely. When you have like a very complex line, a very convoluted line for regression, you can also describe the training set completely. But then the test errors, the errors made on the test set, tend to start increasing after some point. And where you want to be is on that model that is, let's say, able to lower both or the sum of the errors in the best way. But this total error is a sum of these bias and these variance errors. And where exactly you are finding the best one is not always simple. It requires training and it requires a lot of experimentation. I already said this before. I mean, it's always better to have a too complex classifier. So that's why you have instruments to measure like the depth of your tree, for instance, or you can also decide how many clusters you want to have, and these decisions will make your classifier become not too complex. But one thing that is always bad is to have insufficient data. So the quality of your predictors is never going to be high if you have very small data sets. So what have we learned? We have learned that quality of fit in your training set does not measure the forecast accuracy, that complex models can be overfitting, which will also reduce the forecast accuracy. Simple models can be underfitting, also reducing the forecast accuracy. So the best trade-off is related to lowering bias and variance, and it's always good to use your historical data both for the sake of test and training purposes. So, okay, let's use the last minutes to have a very superficial introduction to deep learning. Very superficial because this is, of course, something that can take a long time to really understand, but I want to give you an idea what is behind deep learning. What is behind deep learning is something that enables learning actually to be made fully automated by the computer. That's, of course, the benefit that you get. You do not need a lot of human intervention to have the ability of a predictor to become able to do, for instance, very sophisticated classifications like this picture, is it a car or not a car, these type of things. So when we are doing machine learning, like clustering, regression, and classification as the examples, you always have the analyst, that's you, who does like future engineering or future extraction, and it does a lot of, it takes a lot of decisions before he creates his own classifier. Deep learning does it fully automated. And how does that actually work? Well, it starts with the principle of a perceptron. A perceptron is a mathematical construction that has a number of inputs, and in this case, it has one single output. It will say whether some kind of category is present in this data or not. And it is a very simple formula. It is a weighted sum of the inputs, and then there is a kind of another function applied to this weighted sum of the inputs to decide whether the result should be true or false. This perceptron is a simple thing, and it has limited abilities. But once you combine perceptrons in a way that these ones are going to take as inputs the outputs of the previous ones, then you create what we call a network. And the network is organized in layers in the sense that those perceptrons that take inputs from the same level are considered to be in the same layer. So these are all taking inputs from the data set itself. And then these are creating outputs that are all taken as inputs by these ones and so forth. And the more the layers you have, the deepest your network. And once you have such a multi-layered collection of perceptrons that have these relationships among themselves, if you are able to train them, and what is the process of training? Is the process of giving these weights here that actually define this linear function. To define the proper value of these weights is what the perceptron needs to learn from the data. And all these perceptrons on the network need to do that collectively. Suppose that you can do it, then this network becomes able of processing things like this collection of numbers. So each of these x1s, x2, and x3 is one of these individual cells on this table. And of course, that you have as many as the number of pixels on this picture. So then you already see that the highest the resolution of your picture, the heaviest your network will be. So in fact, typically, these picture recognition algorithms are first reducing the resolution of the picture to the number of inputs that it really has, and then it feeds that collection of numbers through the network, and then there are different predictors. And the different predictors are in the topology of the network. That is like the probability that you have an A, the probability that you don't have an A, and then the probability that you have a B, and so forth. So the layer itself, the network itself is trained for one single objective, like in this case, character recognition. And the process of training, we will get there later, but the process of training, as I said, is to compute those weights, which were W's on the previous slide and omegas here. It's from a different slide deck, but it's the process of computing these weights in such a way that the network is the best in position of translating the training data set to the correct labels. So there is a whole collection of pictures of letters, for instance, and once this has been completely trained, then you are identifying the A's correctly and the B's correctly and the C's correctly and so forth. Designing such a network is a function of defining how many layers it will have, and what is the function that translates these linear sums into the inputs of the next one. One typical function is a so-called ReLU, which is the max of 0 and the number, which says that for positives it's 1 and for it's x, and for negatives it's 0. But this formula does not work all the time because it's not differentiable. So you have also sigmoid formulas, and there's other so-called activators or activation functions. So you designing this is a lot of choices, but once you have chosen the topology of the network, it will learn by itself. And it learns by applying a principle which is called gradient descent, in fact, which is actually a principle that will solve an optimization problem. It will minimize the loss function, and the loss function measures the errors made by the formula. And yet each time that this function is minimized, the thetas or the weights of the network will be modified in such a way that each time the errors will be less and less. So this is basically what happens in deep learning. The number of weights, because the network can be very complex, the number of weights is very high. The number of operations that needs to be made is also very high. The size of the data sets is very big in general. So therefore, this is a very computationally intensive thing. And it only became possible nowadays because we have arrays of processors that work simultaneously. And typically, this is done on graphical processing units, which are collections of processors that do simple things. Unfortunately, these operations are in fact simple. So these are simple operations that need to be repeated many, many times for many usually big data sets. So it takes a lot of time to train, but it takes very little time to apply. So once the instrument is trained, it will give predictions in almost no time. And what is the mathematics behind all these? Why is this important? What is the benefit of doing all these? Well, the thing is that somebody proved the so-called universal approximation theorem, which says that if you have such a network like this, even with one single layer, not even a deep one, that translates some inputs into some outputs, you can actually learn any function. So the assumption is there is a function that will translate a picture into the notion it is an A or a B or a C, or there is a cat in the picture, or whatever. There is a function. I just don't know the function. So there is this theorem that says that you can always approximate such a function by computing the proper weights. And that is very well explained in this article, by the way. And you can see it because if you are using the ReLU activation, which is the max of 0 and the number, so that's formulas like this one, then the approximation is going to be like a piecewise approximation of this function, and you can do this piecewise approximation as tight as you want. It's even more dramatic, in fact. If you allow your approximation to be like a stepwise approximation, it can be done by a tree. So in fact, the universal approximation tree also says that a single decision tree can approximate any function. But of course, a tree can be very, very complex. So this is the reason why, and these are the different activation functions with different properties. And all the activation functions that are differentiable, that are smooth, that don't have like these corners here, are typically better because they learn better because it's gradient descent. It requires differentiability, so therefore you need those smooth ones. Okay, in order to finalize this, what is the importance of all these? Well, while people did not have access to deep learning, people were trying to do like facial recognition with feature engineering, like with instruments like classifiers, for instance. Okay, am I seeing two eyes? Am I seeing a nose? In that case, it is a face. But this feature engineering and creating like classification trees or whatever was always failing. And since we became able to train deep learning networks, this happens by itself. The drawback is that it is highly not interpretable. So we are doing very, very accurate classification, but if interpretability is very much required, so this is almost a no-go, but it is the best we can do. And in fact, there are already ways to extract information about how the network learned. So we end up noticing that some layers specialized on contours, some layers specialized on faces, some layers specialized on maybe even like what type of animal has that face. But this is some things that we can discover after the whole process has completed. It does not explain how that happened. That's all very mysterious, but all very powerful and very intriguing, in fact. So this is about deep learning. Let's move deep learning in the labeled set, in the supervised way, like a big collection of pictures, all of them with labels. There is a face, there is not a face, these type of things. And then people nowadays see things happening that I still consider amazing, like the algorithm can do much more than just saying there is a girl on the picture. It can say that there is a girl on the picture playing with a black tennis racket and there is a yellow ball. So it can take a complete narrative of your picture. And this is a collection, of course, of different algorithms that collaborate together. And then you see things like these captions are all generated on the internet. There is a site to which you can actually upload pictures and tell you what it is there. So, for instance, in this case, a man in black shirt playing a guitar and so forth. The computers can do this nowadays, and it's all deep learning. And to finalize, let's tell you how computers can learn if there is no data. And you may think, well, but you told me that machine learning requires data. Yes, but if you do not have data, but you know the rules that the data should obey, you can simulate that data. And that's what is called reinforcement learning. Reinforcement learning actually is based on a very simple idea. You just do something. You don't have data. Remember, you don't have data. You just do something. And then you observe what is the result of what you have done. The algorithm generates a kind of a scenario, and then it measures the effect of that scenario. If the algorithm is happy with the outcome, it will make sure that what was done will be very likely to be done again. So in fact, it's going to increase some probabilities inside the algorithm, the probability that it's going to repeat that. If the outcome is bad, it's going to decrease some probabilities in order to see that happening less often. So this is a very simple explanation of what reinforcement learning is. And by the way, this book does not exist. It's here just for the sake of, as far as I know, it does not exist. But the collection for dummies, it grows very fast. So maybe there is already a book called Reinforcement for Learning. And then you just repeat this. And it may look very abstract, but let's make it more concrete. One of the first examples of application of reinforcement learning is an algorithm that is able to learn these very old arcade games, these so-called Atari games, because Atari was one of those brands that made these games in the past. This game here, it is a simple game to play. Of course, it requires to have some skills. I mean, you move that bat, and that bat on that horizontal bat moving there, it will block the motion of that ball. And if the ball hits your bat, it will go back and it will destroy the wall. It will take a brick out of the wall. If you do not put the bat on the proper place, the ball disappears and you lose. So there are only a few things that you should do to play the game, and it's just moving left or right. And left or right needs a kind of time to reach the place that you want to be. So you need to anticipate whether you are going to go left or right on time. It's not like the bat appears exactly what you want. It's a motion. So the computer was actually instructed to learn that it should go left or right, given a picture that describes the present situation. And it was also told how to value the result of the decision. And that value, it's called a reinforcement, is going to say, well, what you did is good or what you did is bad. And then it learned by itself. It was not told the rules of the game. It was told that the choices were left or right and what to do. And then it learned how to play the game. And you may think, okay, well, that's fun, but is that all? Well, the next example is also a game, but a little bit more complicated. And I don't know if you ever played Pac-Man. I did, and I still do. And if you look at this this video is going to tell you how this algorithm actually works. It's also reinforcement learning. So basically, what it does is that each situation becomes a picture. The dimension is also reduced because it can be just a collection of simple pixels. And after a few iterations, you saw what it did when it was just starting to learn. This is after a few iterations, it starts to play better and better. You did not tell it how to play. You just told this algorithm that it can go up, down, left, right, or stay where it was. And then after 5,000 iterations, it learned that it could even eat the enemies after eating one of those power pills, and it started winning most of the games. And this is indeed an example of reinforcement learning, learning without data, just with some rules or some way to simulate your I want to go to my next slide, not to my next video. Let's go to the next slide. Okay, I think I probably need to stop my presentation and restart it again after that slide. So the video captured me. It's always bad with videos. And the most well-known application of reinforcement learning, and that's actually when this methodology reached main use, is when a computer did something that was considered to be undoable, and that was that it learned to play the game of Go to such an extent that it beat the champion of Go. Before that, we were already able to beat the chess champion, but the game of chess is much more, in some sense, much more structured than the game of Go. In the game of Go, things may change dramatically in one single set. And that was making the reasoning that was applied to beat the champion in the game of chess, which is very feature engineering. It's just like you are at some set in a game of chess, and the computer thinks, if I do this, what happens in a few moves? If I do this, what happens in a few moves? And for all this kind of what-if analysis, is going to take the best set. For the game of chess, that takes a huge amount of computations and a huge amount of memory, but is doable in some sense. While for the game of Go, it's not doable because the computer can just not cope with all these possible follow-ups from each given situation. But what deep learning taught this computer to do was to be able to predict which parts of this kind of tree, this tree that analyzes all these what-ifs in the scenario, which parts of this tree were more promisable, and preventing the computer to need to explore the whole tree, which would be undoable. And people believed that this was actually impossible to achieve until indeed the world champion of Go lost to a computer. So that's the moment that deep learning became very, very popular. And nowadays we see deep learning almost everywhere. Actually, many cars that claim to be able to self-driving learn that by deep learning and all that type of stuff. So I end up finishing on time for a few questions and just some announcement. What are we going to do on Thursday? We are going to move a little bit up, and we will go to prescriptive analytics and to mathematical optimization. So basically what we did together today, we started at the descriptive analytics, we went a little bit towards the diagnostic, the predictive, and we end up here. And it will take us just a few hours. So of course, it's just an introduction, but there will be a moment that you will be doing your own projects, and hopefully that will be a moment for you to consolidate all this knowledge. Okay, so we have like 5 minutes before we reach the hour that we were supposed to stop at. So please unmute if you want to say something. I also see that there are some things in the chat. So a question, can I say that neural networks are perceptrons? Well, you can say that neural networks are collections of perceptrons organized in some way. Each of the individual nodes is a perceptron, and a network is like a combination in the sense of mathematical combination of functions, combination of perceptrons, because one perceptron takes variables as input, it's like a function. It gives values as an output, it's like the result, and then the next perceptron takes the output of the first as part of its input. So it's like a composition of functions organized in a network. So the network, the neural nets consist of perceptrons plus the connections between the perceptrons. Are other projects that use reinforcement learning other than games? Yes, there are. My examples were only games because games are actually easy to understand and also impressive to see how the computer learns how to play them. But there are reinforcement learning applications, also in optimization, by the way. Maybe I can refer to some of them on Thursday, maybe, but I should not put too much on Thursday because I also want to tell you something that I think it's really useful. But you can also learn using reinforcement learning how to optimize, or how to take those decisions that are the best course of action. And that can, of course, be inside a game, but it can also be something like, where should I put my next hospital, or something like that. I have a few choices, and each of those choices costs some money. They have some benefit because they serve part of the population. That can also be done with reinforcement learning. On Thursday, we will learn how to do that with mathematical optimization, which is much more predictable, by the way. Can you use reinforcement learning for geospatial data? Yeah, well, you can use reinforcement learning for almost everything. If you mean by reinforcement learning used in geospatial data, things like, for instance, detecting whether a road is present on a picture on satellite imagery, probably yes, but I think that most often is done with labeled data, like you have already a few examples of roads detected on satellite imagery, and you use them to train a model that will detect other roads or other things, or the existence of homes somewhere. But you can definitely use machine learning for geospatial data, that's for sure. There are also other questions that you may need to answer with geospatial data, like, for instance, you have many different suppliers of geospatial data, like road networks, one road network from OpenStreetMaps, another road network from some local municipality that has some kind of very accurate road network, and you want to merge them together. It's not very easy because sometimes there are just some small errors in the coordinates, and you do not know whether you are looking at the same point or not. Of course, machine learning can help there as well. I think I skipped one. Would you share any free sources, trainings to go deep, learn about these topics? Well, there are already some links on my slide decks and also some references. Depends on where you want to go deep. If you want to go deep on deep learning, I have excellent references that I can share. They are really good books. Please just let me know either on Slack or on an email what you are really looking for. I can share links for everything, but I think it will be easier if you can tell me your specific interests, and then I can do it in a more accurate way. In machine learning, can we use different types of regression, like logistic? Oh, yes. Of course, you can use logistic regression. Yes, I did not mention it. I decided to keep my examples simple, like just linear regression to estimate values. Well, logistic regression is a way to use regression to estimate like truths or falses in something like that. It's like almost a combination of classification and regression. Yes, you can do it, and there are much more machine learning instruments than those that I have named. Yes, it's a very complex and rich world. I just wanted to give a very brief introduction to the concept of supervised and unsupervised learning, and the difference between machine learning in the classical sense of feature engineering and what deep learning entails. And that was also very ambitious for just a few hours. I see that the chat has stopped growing. Any additional question or remark? Well, thank you. You are very welcome. And I'm looking forward to being with you on Thursday again. Thursday will be a new topic. Any other thing? Thank you. You are very welcome. All right. Oh, you very, very kind. This was very helpful, very kind. Okay, please feel free to use the slides. Please feel free to use the notebooks for your own experiments. Please feel free to reach out if you have any additional questions. I will try to answer all the emails you may send or all the things I see on Slack about these lectures. Well, feel free to ask and feel free to try to use these to your own benefit, on your own data, on your own projects. I'm looking forward to your project phase. I may or may not be involved mentoring you, but anyhow, it has been a pleasure. I wish you a great weekend to all of you. And I'm looking forward to the next episode on Thursday on mathematical optimization. Bye-bye.
Bye. Thank you. Have a lovely night.
Bye-bye.
Bye-bye.
See you. Bye-bye.
Thank you very much. Bye-bye.
You're welcome.
Bye-bye. Bye-bye.
Bye-bye. I will stop recording now.